Welcome to Selection with Sathi. Today we cover divide and conquer, one of the most fundamental algorithm design paradigms. We will learn the general template, then deep dive into merge sort, quick sort, the master theorem and recurrence relations, all with code on screen. This is a high-frequency topic in GATE CSE and coding interviews. Let us begin. The divide and conquer paradigm has 3 steps. Look at lines 4 and 5. First, divide the problem into smaller subproblems. Usually we split into 2 halves, but it can be more. Lines 6 through 8, conquer by solving each subproblem recursively. The recursion bottoms out at the base case on lines 2 and 3. Lines 9 and 10 combine the subsolutions into the final answer. The key insight is that subproblems must be independent. If subproblems overlap, use dynamic programming instead. The time complexity depends on how many subproblems we create and how much work the combined step takes. Merge sort is the classic divide and conquer sorting algorithm. Look at line 4, divide the array at the midpoint. Lines 5 and 6, recursively sort the left half and the right half. Line 7, merge the two sorted halves. The merge function starting at line 9 uses 2 pointers. Lines 12 through 16, compare elements from both halves, always picking the smaller one. Lines 17 and 18, append any remaining elements. The merge step takes O of n time. The recurrence is T of n equals to T of n over 2 plus O of n, which gives O of n log n. Merge sort is always O of n log n, regardless of input order. Quick sort uses a different divide strategy based on partitioning. Look at line 3. The partition function chooses a pivot and rearranges the array so that all elements less than or equal to pivot are on the left and all elements greater are on the right. Lines 4 and 5 recursively sort the left and right partitions. The partition function starts at line 7. Line 8, we use the last element as the pivot. Lines 10 through 13, scan through the array. When we find an element less than or equal to pivot, increment I and swap it to position I. Line 14, finally, place the pivot at position I plus 1. Average case is O of n log n, but worst case is O of n squared when the pivot is always the smallest or largest element. The master theorem solves recurrences of the form T of n equals a times T of n over b plus O of n to the d. Here, A is the number of subproblems, b is how much the input shrinks, and d is the exponent of the combined step. First, compute log base b of a, case 1. If d is less than log base b of a, the recursion dominates. T of n equals O of n to the power log base b of a, case 2. If d equals log base b of a, the work is balanced across levels. T of n equals O of n to the d times log n, case 3. If d is greater than log base b of a, the combined step dominates. T of n equals O of n to the d. This is the most important theorem for gate recurrence problems. Let us look at common recurrence relations. Binary search, T of n equals T of n over 2 plus O of 1. Here A is 1, B is 2, D is 0. Log base 2 of 1 is 0, equals D. Case 2 gives O of log n. Merge sort, T of n equals to T of n over 2 plus O of n. A is 2, B is 2, D is 1. Log base 2 of 2 is 1 equals D. Case 2 gives O of n log n. Strassen's matrix multiplication T of n equals 7 T of n over 2 plus O of n squared. A is 7, B is 2, D is 2. Log base 2 of 7 is about 2.81, which is greater than 2. Case 1 gives O of n to the 2.81, which beats the naive O of n cubed. Always identify A, B, and D first, then apply the correct case.
Let us trace merge sort on the array 38, 27, 43, 3, 9, 82, 10. Split into left 38, 27, 43 and right 3, 9, 82, 10. Left splits into 38 and 27, 43. 27, 43 splits into 27 and 43. Both single elements, already sorted. Merge 27 and 43, compare 27 and 43, 27 is smaller. Result, 27, 43. Now merge 38 with 27, 43. Compare 38 and 27. 27 first, then 38, then 43. Left half sorted, 27, 38, 43. Right half, 3, 9 splits and merges to 3, 9, 82, 10 merges to 10, 82. Merge 3, 9 and 10, 82, gives 3, 9, 10, 82. Final merge, 27, 38, 43 with 3, 9, 10, 82. Compare element by element, 3, 9, 10, 27, 38, 43, 82. Sorted. Total work, n log n. Now let us trace quicksort partition on array 10, 80, 30, 90, 40, 50, 70. Pivot is 70, the last element. I starts at -1. J equals 0, 10 is less than or equal to 70. Increment I to 0. Swap a 0 with a 0. No change. J equals 1, 80 is greater than 70. Skip. J equals to 30 is less than or equal to 70. Increment I to 1. Swap a 1 and a 2. Array becomes 10, 30, 80, 90, 40, 50, 70. J equals 3, 90 is greater. Skip. J equals 440 is less than or equal to 70. I becomes 2. Swap a 2 and a 4. Array 10, 30, 40, 90, 80, 50, 70. J equals 550 is less than or equal to 70. I becomes 3. Swap a 3 and a 5. Array 10, 30, 40, 50, 80, 90, 70. Finally, swap a 4 with a 6 to place pivot. Result 10, 30, 40, 50, 70, 90, 80. Pivot 70 is at its correct position, index 4. Let us solve the recurrence T of n equals to T of n over 2 plus O of n using the master theorem. This is the merge sort recurrence. Step 1. Identify the parameters. A equals to the number of subproblems. B equals to the factor by which we divide. D equals 1, the exponent of the combined step. Step 2. Compute log base B of A, log base 2 of 2 equals 1. Step 3. Compare D with log base B of A. D is 1, log base B of A is 1. They are equal. This is case 2 of the master theorem. Case 2 says T of n equals O of n to the D times log n. So T of n equals O of n times log n. We can verify there are log n levels in the recursion tree, and each level does O of n total work. N times log n correct. Maximum subarray sum using divide and conquer. Array -2, 1, -3, 4, -1, 2, 1, -5, 4 split at midpoint index 4. Left half -2, 1, -3, 4, -1. Right half 2, 1, -5, 4 recursively. The left max subarray is just 4, giving sum 4. The right max subarray is 2, 1, giving sum 3. But let us check, it could also be just 4. Now the crossing subarray, expand left from mid. Start at index 4, value -1. Then include index 3, value 4. Sum is 3. Expand right from mid +1. Index 5 is 2. Index 6 is 1. Sum is 3. Crossing sum is 3 plus 3 equals 6. The maximum is max of 4, 4, 6, which is 6. The answer is 6 from the subarray 4, -1, 2, 1. This divide and conquer approach is O of n log n.
Quick exam tips. First, always identify the three parts of divide and conquer: what to divide, how to conquer, and how to combine. Second, the merge step determines the overall complexity. O of n merge gives O of n log n total. O of 1 combine gives O of n total. Third, use a randomized pivot in quick sort to avoid the O of n squared worst case. Random pivot gives expected O of n log n. Fourth, for gate recurrence problems, identify A, B, and D from the recurrence, then directly apply the master theorem to determine the correct case. For more DSA concept videos with code walkthroughs, download the Selection with Sathi app. Like and subscribe. Thank you.